And I just want to say thanks to all you guys for showing up today. We had a great professional development seminar last year on wet snow, and Scotty's done an awesome job putting these things together, so I think we all owe him a round of applause to start the day out. But it's just fun to get together and talk about some of this stuff as a group, and I think that, you know, as a crew here, we're all going to know a lot more than any one person in the room. I know there's a couple people in the room that know a lot more about me than, or a lot more. But I really want them to tell the rest of you. Know a lot more about fracture mechanics than I do, and a lot of you have been out in the snow. You know a lot about fracture mechanics that you may not even realize. So, you know, as I go through, you know, in particular this talk, but also throughout the day, like if something doesn't make sense to you, either from a scientific perspective, if you're a scientist, if something doesn't make sense to you from a practical perspective, it doesn't match with some of the things that you see out in the field, then holler, let's discuss it and try and make sense of what we're seeing, or understand that there are certain things that we maybe can't make sense of yet. So Scotty just asked me to kind of lay a little groundwork for the day by talking about some basic fracture mechanics and the implications for post-control release. So I'll talk a little bit about fracture mechanics, and then I'm going to try and tie that into what are some possible reasons for post-control releases that we see. And before I get going, I'll just thank a few folks. Ron Simonhoys, who I think many of you know, who I've done a lot of work with on fracture propagation and on the extended column test, and Joachim Heierle, who did a bunch of work on the anti-crack. And we'll talk a little bit about that. And then Alec, who's worked a lot with Joachim and done some real interesting work, and I'll be referring to some of the work that Alec and Joachim have done. And yeah, we'll leave it at that. So let's start out with, you know, we're talking about slab avalanches, not loose snow avalanches. So let's start out with a slab avalanche. You know, a nice small slab avalanche. Probably several of you have seen this before. This is an amazing feat of riding. We'll watch this guy. He's going to ride all the way to the bottom through the back side of the slide. See, here he comes. There's no stopping him. He's right there. He's coming out the bottom here. Yeah, see, there he is. There he is. Try and do that on a pair of fat skis, huh? So that's what we're talking about, slab avalanches. You know, how do these slab avalanches occur? What's the mechanism for them?
Where was that?
That was Clementia or something like that up in BC. I'm not sure if we're going to hear this quite well enough.
Unbelievable.
Let's see if we can hear this next.
The whole goddamn thing went A.
I love that line. The whole goddamn thing went A. So, in our basic avalanche classes, we talk about slab avalanches, and we usually say, you know, you need for an avalanche, you need a slab, you need a weak layer, you need a slope, you need a trigger. All right? But we know that we have slabs, weak layers, slopes, and triggers all the time, and we don't get avalanches. Right? So we're going to try and take a step in further and look at fracture mechanics in a little more detail. Avalanches start as cracks. Okay? Cracks in the weak layer. And for a crack to become a concern, it must not only initiate, right? We first need to initiate the crack, but then that crack has to propagate to some critical size. And at that point, then we can talk about propagation and whether or not it avalanches. That's one of Ron Simonhoys' famous ISSW slides. So I'm going to go through just some general definitions here so we're all on the same page. First of all, and I think most of these are pretty simple and we know what they are. Slab, it's a relatively more cohesive layer in the snowpack. Okay, the key here is relatively. Now, For post-control releases, what kind of slabs do we usually see? What are the characteristics of a typical slab associated with a post-control release? Hard slab. Yeah. They tend to be probably harder and maybe deeper than we're used to, right? So, often hard and thick for post-control releases. Weak layers, relatively less cohesive. And for post-control releases, what kind of weak layers?
Persistent.
Yeah. We tend to see persistent weak layers. Okay, often facets, depth hoar, surface hoar, that sort of thing. For avalanches in general, you know, this relatively more cohesive and relatively less cohesive is important because we can have cases with very weak slabs that are still capable of propagating fractures or propagating cracks and causing avalanches. Okay, we got a video here from Bruce Jameson's group, and talk about a couple more definitions. One is what a crack is versus a fracture. Okay, a crack is a physical break in the snow structure. All right, so it's actually a physical break. The fracture, we've often talked about fractures as a break, but in fracture mechanics lingo, a fracture is actually a propagating crack. So when you say a fracture to someone in fracture mechanics, they're thinking about a process. They're thinking about an actual propagating crack. And so I'm going to try, even though within the snow group we've often talked about fracture as that crack, I'm going to try and keep that terminology more or less clean, or as clean as I can, given that we've used these terminology for a while. But that crack is that initial the initial debonding of a layer, and then the fracture is actually the fracture is the propagation of that crack. And so here we'll see both of those in action. So we got a crack, and then when it gets to a critical length, it propagates. We got the propagating crack or a fracture, and then it slides. Okay, weak zones. What are weak zones? Deficit areas, sweet spots. Anybody have a good definition for that? We used to call weak zones, whoops, I went one too far. We used to call weak zones as a place where the shear stress exceeded the shear strength. Okay? But we've come to look at avalanches differently in the last 5 or 10 years, depending on who you talk to. I think still some people would probably pop that definition up there, but there'd also be a whole crew of people that would look at things differently. And I think that definition might not strictly hold under the way we look at fracture mechanics right now and the way that I'm going to talk to you about fracture mechanics today. And so really, in terms of weak zones, I'd like to just talk about them in real general terms. In the general terms of a relatively weaker area of the slope, or an area of the slope where you'd be more likely to either initiate and or propagate crack. Okay? By propagating that crack, you're more likely to trigger an avalanche from that area. So we'll just talk about it in that more general term. And then you'll also hear us throw around the term spatial variability. Usually spatial variability, you have to attach some kind of scale to it. Are we talking about a whole mountain range scale? Or are we talking about individual slopes? But in terms of fracture mechanics, in terms of avalanche release, we're really talking about spatial variability just on that slope scale and how much variation occurs. And you're all field people. You all know that there's a heck of a lot of variability out here. And this is just a great graphic from Cam Campbell and Bruce Jameson. And each one of these numbers is a Roosh block score. And they come all across the slope. You can imagine how many Roosh blocks they dug. But you see there's 2s, there's 4s, there's 7s. So a really wide range of variability in terms of how easy it is to get that Roosh block to break, and maybe how easy that Roosh block slides off. Okay. All right, so there's just some general definitions to lay a little groundwork for you. And Alec gave a talk a couple weeks ago at MSU and talked about fracture mechanics and in a little more detail talked about these different models. Now, the model that we used to, or the model that was generally accepted for fracture mechanics for quite a long time for snow is McClung's shear model that he introduced way back in the 1970s. And the driving force for the propagation here is the slope parallel component of gravity. And with the shear model, it's not possible to have whoops on flat terrain, okay, with that shear model. And that was one of the shortcomings of that model. Now, more recently, Joachim has done a bunch of work on what's called the anti-crack model. And you can just think of that as collapsing snow. And people have talked about collapsing snow and looked at collapsing snow for years and years. In fact, back in the 1960s, Charles Bradley was doing experiments on collapsing snow here at Montana State and up at Bridger Bowl. All right? Well, what Joachim has done is he's really formalized that and quantified that and explained it in a lot tighter package. And this, the anti-crack model is really looking at using this collapse of, the collapse is really the primary force that drives the fracture. Okay, so you have the collapsing of the weak layer and then the communication of that collapse through the slab, and that just keeps that thing going. And we'll talk about that in a little more detail. I'm just going to now give you some of the evidence for the anti-crack model to give you an idea of why I think that that's the model that we should be using when I talk about fracture mechanics for the rest of this talk. So some of the experience, we actually see collapses when we're out in the field. This is a video, or a slow motion video of Ron Simonhoy's doing a large extended column test, and you can, I mean, I don't think I need to convince you that you can watch that collapse wave come right across that block. Boom. I think the most obvious experience for, or the most obvious evidence for the anti-crack model is just the fact that we get whoops going across flat terrain. This is a picture from Chris Lundy at the Sawtooth National Forest Avalanche Center, and he's triggered something like 7 different remote avalanches from hundreds of yards away in the flats. Well, the only way for that fracture to get across there is some kind of collapse coming from his skis and going boom, 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 right up the slope and then triggering those slides. So that's more evidence for the anti-crack model. Now, Alex done some really nice work looking at fracture propagation in long columns. And one of the things that he showed was that the collapse, he actually tracks all these little dots, and what he's shown is that the collapse precedes the shear in his experiments, which is good evidence that collapse is the primary driving force here for the fracture. And he's also measured fracture speeds that are consistent with collapse. If you go through these two different theories, the shear model predicts fracture speeds of 1 order of magnitude, and the collapse model has actually quite slower fracture speeds. And Alec measured some fracture speeds in these long beams, and they were consistent also with measurements that Crane Johnson and Bruce Jameson measured in some flat fields. They measured some whoops up in Canada. So that's just more evidence for the anti-crack model. And finally, the anti-crack model and the shear model have very different predictions in terms of what the slope angle effect should be for skier triggering and what the slope angle effect would be on your stability tests. You don't have to worry too much about these numbers, except just understand that these dotted lines represent the shear model and these solid lines represent the anti-crack model. This is the slope angle across the bottom, and this is sort of increasing difficulty of triggering, let's call it, as you go up. And so what it shows is that it's very difficult to trigger something with the shear model at lower slope angles, but as we get higher and higher slope angles, it's much, much easier to trigger things. On the other hand, with the anti-crack model, it's fairly similar until we get out here, you know, around 60 degrees or something. It's fairly similar, and so...
What are the two colors?
What's that?
What are the two colors?
Oh, I forget. It was 2 different assumptions. Do you remember, Al?
Is this your ISW stuff?
That was Joachim's.
Isn't that like where you are compared to the crack? Wasn't that?
That might be it, yeah.
Doesn't really matter.
Yeah. It's just the pattern that's important. But you'd think I'd remember that since I was a co-author on that paper. I probably understood less about that paper than most papers that I've done. So here's some data that we collected down at Lionhead last year. And this is on this axis we have the tabs to get an extended column test to propagate all the way across the column. And here we have the slope angle. So we're going from about 14 degrees up here to about 35 degrees. And as you can see, there's really not much of a trend. If anything, there's a slight increasing trend. The shear model would predict a pretty rapid decreasing trend across these data. And the anti-crack model would predict that the data would look quite similar to that. So we have a lot of good evidence for the anti-crack model. One of the things that people have brought up again and again is we see all this good evidence for the anti-crack model, but all the evidence is usually collected, or all the data has been collected with persistent weak layers. So we've looked at surface hoar, depth hoar, and things like that. So one of the things we've been trying to do is collect data in non-persistent weak layers. And so thankfully for me, Ron Simonhoy's moved from an area with very persistent weak layers to an area that doesn't always have persistent weak layers, and he's now in Alaska. And here's Ron on a test slope in the middle of a raging blizzard, and he went out and did 14 extended column tests. This is just about a month ago, in Alaska, on varying slope angles with a storm-snow interface. In fact, they went there, they collected these data. The next day, they went back and they tried to get these slopes to avalanche with a bunch of explosives, and they couldn't get them to avalanche. So it was a very, quick instability. But this is what his data looked like for a non-persistent weak layer, one that we don't typically associate with collapse. And, Joachim makes the point that really the magnitude of the collapse that we need to drive this fracture is very, very small, like on the order of a crystal size, maybe a millimeter. So that we can actually be having these collapses, we just don't notice them as much as we do with persistent weak layers. So what this suggests then is a lot of evidence that the anti-crack model is really the model that makes the most sense for us to be looking at. So I will just really be talking about that. Any questions so far?
What was the instability that they were looking at there? Was it just upside down snowstorm, or?
Yeah, just some little break in the snow. I don't know exactly. I got a snow pit of it. I think it was just, just one of those kind of subtle storm snow interfaces. Yeah, Jeff.
Well, it seems like under that assumption, you wouldn't have to get on slopes steep enough to avalanche to come up with a quantifiable extended column test.
Yep, that's exactly right. So the practical implication of this work is that you can do your extended column test, or maybe perhaps other stability tests too, in flatter terrain. And one of the things that got us looking at this was the fact that Dave Gaudier and Bruce Jameson had done some initial work looking at the propagation saw test, and it's shown that with the propagation saw test that there didn't seem to be much of a slope angle effect. So we thought, there's no slope angle effect with that. I wonder if we're seeing it with this with the extended column test. But yeah, it means that as long as the key there is you still have to have a snowpack that's similar to what you're going on to. So
Karl?
Yeah.
Quick question.
Yeah.
So the anti-crack model depends on kind of some normal loading to get this fracture to propagate. You get some sort of loading associated with a critical crack size.
Yeah.
And it's able to propagate. But to get and you guys talk about this, to get then some sort of an avalanche on the slope, the shear is still important. I mean, you talk about the fact that it's overcoming friction. I don't know if you're going to talk about this.
Yeah.
Slab overcomes friction, but basically that's a shear component. So once you have this collapse, the shear is still a relevant parameter.
The shear is definitely a relevant parameter.
So
yes.
It's something I'm going to talk about a little bit.
Yeah.
When we talk about applying explosives, is that we get both those loading scenarios from explosives. So.
Yeah. Yeah. No, the shear is definitely important. I guess
after the crack is.
Yeah, I guess that's what we're trying to figure out. Is what's driving that fracture, and it
Right.
seems like the evidence thus far, anyway, is supporting the idea that the driving force for that fracture is the collapse.
Yeah, no issue with that. I'm just saying if you want to initiate, because we're talking post-control base and avalanche, the shear part's still going to be important.
Oh yeah.
To get it to move.
Yeah, you got to get it to move. So yeah, you come down to these. That's perfect lead into this. For an avalanche, these are the things we need. All right, we need to somehow initiate a crack in that weak layer. And then that crack needs to grow to a critical size. And by a critical size, I mean it needs to get out to the size at which it can become, that we can start crack propagation, that it becomes self-sustaining in terms of the propagation, in terms of propagating outward, in terms of fracturing. So we get this crack initiation, this crack growth to a critical size, then we get crack propagation, also called fracture, and then to get an avalanche, we need to overcome the friction on the slope. Okay? So we basically kick the legs out from under the whole slope, and then if we're not on a steep enough slope, if we don't have a smooth enough weak layer or whatever, that slope may just stay in place. If we're steep enough, then the snow will slide. Okay? And I'm going to go over each of these in detail. The idea here now is I want to go over each of these points, and then we want to talk about the possible implications for post-control release of each of these points. All right? So here's some slides that Eric Knopf gave me from Snowbird. And explosive goes off. Okay, have we initiated a fracture? Next slide. We now know that we've not only initiated a fracture, but look at this. Looks like the fracture, we see some stock walls building up. See some stuff. So not only have we initiated a fracture, look at the stock wall right here, but that fracture is obviously propagated. If we initiate the fracture went to a critical size, it then propagated, and now the next question you have to ask yourself is, are you on a steep enough slope to overcome the friction? And yes, we are. Okay? Another slide from Snowbird, but one of the things that I want to bring up is this idea of successfully mitigating avalanches. Norm Wilson used to always say, and Larry Haywood has talked about this again and again in his talks, is that in order to successfully trigger avalanches, you need to place the right charge in the right place and do it at the right time. Okay? Right charge, right place, right time. And I'm going to try and blend that into our discussion too. I mean, clearly we've got some shot holes up here. If you'd done those shot holes and then just assumed that the slope was stable, you'd have been wrong. In order to get this avalanche, that shot needed to go into the right spot to trigger the avalanche. You needed to have the right charge. It needed to be big enough and placed in the right place that it actually initiates that fracture, and that fracture becomes a critical size, and your timing needs to be right too. Okay, in terms of crack initiation, if we look at naturals, these cracks can initiate due to, maybe a flaw or variability, and then they might grow due to, say, increasing load or creep. So a natural avalanche, it's a really different situation than what we're looking at with post-control releases. Maybe the slow growth of this initial crack until it gets big enough, and once it gets big enough, then that propagation can start to occur. With triggered avalanches, one of the things that I found interesting, and this is some of the work that Alec did before when he was up in Canada, is that we're commonly initiating cracks beneath our skis. This is a picture of Ron's skis, Ron Siminoy's, and you can see that he's initiating some cracks in the weak layer. And I think more commonly than we think, we're initiating cracks. And with explosives, I'm sure we're initiating cracks too. And so we have to ask ourselves then, if we're initiating these cracks, what's the limiting factor for avalanching? And in a lot of cases, that limiting factor, rather than the initiation, might be the propagation. Okay, we don't know that for sure, but that's something that we should at least entertain, because in the old way of thinking about post-control releases and the old way of thinking about triggering avalanches, it was almost always we need to initiate the fracture. Okay, we didn't think so much about propagation, but I think that propagation piece of the puzzle is huge. Okay, so after we initiate that crack, then the crack needs to grow. It needs to grow to a critical size. And the question's been thrown out there quite a bit. What is the critical size for a crack? Anybody have any ideas? Tens of meters? A couple centimeters?
Depends on the load, right?
Depends on the load. Yep. Depends on the load. And in fact, if given the right load, we may not need to have a crack formed at all. I mean, our load might create the crack and push it out to that critical size, right? So the critical size crack, at least from some of the work with the propagation saw test, would suggest that maybe that critical size of that crack would be on the order of 40 to 80 centimeters. Or somewhere in the area, you hear bantered around a bit, somewhere on the order of the slab depth, you know, general ballpark. So I don't think we really know for sure. For an avalanche, I mean, you can measure what that critical crack length is, excuse me, for a propagation saw test. But we don't know for sure, you know, what it is when you scale that out to an avalanche. Yeah, right.
I'm just thinking about that picture from Snowbird. If that was a big, thick, deep, hard slab you had just earlier, maybe those shot holes weren't. Maybe in this case, it was clearly able to propagate, but it was an issue of getting it to initiate.
Exactly.
In a scenario like this.
Yep. Yep. And I think any time, you know, and I don't know what the history was on this particular slope. I don't know if Eric remembers, or, but
I think it was just one big storm.
One big storm.
They all there.
Do you know if there were any shots placed on this slope before the shot was placed that picked the whole thing out?
I don't know.
Because that's where you really know that, is that, you know, if you, and I'll have a video that Scotty gave me here in a minute, but if you put a shot on a slope and it doesn't go, and then you put another shot on the slope and that shot pulls out your first slope, your first one, then you know that that first one just, you know, that first one just must have not been in the right place to get that thing to go. Because clearly a fracture could propagate through that area. Anything else? All right. So, okay, for the crack growth, the critical crack size on the order of the slab depth, and some of the evidence that we see has shown that skiers and explosives may create critical cracks, especially if you're dealing with a softer slab and a shallower weak layer. You know that those skiers and explosives can reach really easily. And thus, like I said, propagation may be the limiting factor for avalanching in some situations. Here's oh, you gotta be kidding me. What in the world's going on now? I've only run this like 40 times on this computer. Huh. Well. Here we go. So this is one of Alex's videos. And what we're going to see here is, probably a lot of you have seen this already, but it's fracture initiation, but not fracture propagation from a skier coming through. So keep your eye on the dots. You see the skier come through and you'll actually see the crack initiate here, but it won't propagate to the end of the slope. So I don't know about you guys, but that's a little unsettling to me to think that I'm out there skiing, like initiating all these cracks in weak layer all the time. You know, I'm doing what, really? Because it might not exactly match up with the way that we've thought about slides in the past.
Karl, is that an isolated column?
That is, what was it, Alec? I think it's just you know, it's just.
Yeah, we just dug a trench.
Just dug a trench on that side, yeah.
It was the second try, obviously.
That skier wasn't able to trigger the avalanche the first time. Now, was that you, the skier, or you, the filmer?
I filmed.
Okay. I thought so, because the guy was on television. Okay, this is a great, I really like this graphic. This is from a paper that Dave Godier and Bruce Jameson did for ISSW this year. But once we get that crack, so we initiated the crack, then we had to grow that crack out to a critical size. Okay? Then at that point we can talk about propagation. And as Alec was telling me yesterday, he's like, it's all about the slab. And I think that's right. You need a slab that's going to communicate that fracture out and across the slope. And the way that Bruce and Dave put it in their article is they said the energy transfer capacity of the slab, capacity of that slab to transfer energy out, has to be greater than the energy required for propagation. So really all you're looking at is you have a situation that back here we have the fractured weak layer, and the slab is communicating the fact that it's fractured and pushing on the weak layer here. That weak layer fracture continues. Now, one of the things that we see happening with fracture propagation is we've also got cracks going through your slab. So we have slab fractures. If this slab fracture, and what they're demonstrating here is how a fracture could arrest or could stop. So if that fracture, we got a fracture coming through the slab at the same time this fracture is advancing. Now, if that fracture goes through, and this distance right here is less than the critical distance, then the fracture will stop and we'll have fracture arrest. If that's greater than the critical distance, then we'll have a crack there and the fracture will continue. Okay, and Alec talked about this in terms of sort of a race between the fracture within the slab and along the weak layer. So we need an intact slab to communicate that fracture forward. And I think that is important for some of our avalanche control work. Yes?
But we see lots of avalanches where there's tons and tons of tracks all over the slope that's broken up that slab.
Mm-hmm.
So how does that work?
There must still be enough integrity in that slab, to move a fracture through. Well, I mean, like, the stuff on Saddle Peak was obvious because even though we had tracks all over the top of that slab, you still had that hard slab underneath that was capable of being the driving force of that fracture. In other cases where maybe you actually have divots where snowmobilers divoted down all the way underneath the weak layer, then that fracture must travel around that area somehow,
How do you think, when you see avalanches that just zip past rock bands through dense sections of forest, what do you think is allowing it? You thinking that there's just enough connectivity in the slab?
Yeah.
Those regions?
I mean, on a theoretical basis, if you were able to trigger a WUMF on the flats and there was no spatial variability, that fracture theoretically could just travel forever. And so what causes that fracture to stop is variations such that the slab probably loses the ability to communicate the fracture, or maybe the weak layer characteristics change such that doesn't get communicated on either. So in cases where stuff's doing that, I think it's just there must be enough uniformity in the conditions, or the conditions must vary in just the right way to continue that fracture moving through there. Ed, you had a comment?
So is that weak layer has to be thick enough to cause sufficient moment to put the top of the slab into tension? It seems if you're talking about a crystal or two thick is thick enough, it doesn't really jive with that kind of picture, does it?
You mean to actually cause this thing to break? Yeah, I mean if it's not
very small, you got to slap it up.
Yeah, if it's breaking if it's a real thin weak layer, you're probably not going to see that happen. So if you have a thin weak layer and a thick slab, it's likely to propagate a long ways because you're not going to lose.
So a thin weak layer, and then say that it's worse than a thick surface well layer, because that wouldn't put as much of the energy into the slab. I just see it.
Yeah.
Maybe a bit of a,
I mean, makes sense to me. I don't really know for sure, but yeah, Mike.
Seems like we've seen that at Big Sky on the south base when we have a thin weak layer with a thick slab. That's when we get the huge long propagations.
The big propagations,
in
yeah.
general.
Carl, so if we need a cohesive, somewhat elastic slab to really propagate, particularly over long distances, theoretically, tracks on a slope that don't disturb that weak layer, but serve to just compact that slab, could actually contribute to, I mean, this would be, theoretically speaking, like a slope that gets skied quite a bit. And I mean, just looking at the video from the Saddle Peak, where you had that super dense wind slab capping the weak layer, all that, you know, what would be loose unconsolidated snow getting skied over and over again theoretically could create more of a cohesive slab over time. I mean, I guess, obviously very speculative, but the principle, I guess, is kind of turns the whole skier compaction thing on its head a little bit.
I mean, for me, with skier compaction, it's all about whether or not you're impacting the weak layer.
Right.
And if you're not impacting the weak layer, all bets are off. So if you're cutting that weak layer up with your skier compaction, then I think you're definitely stabilizing the slope and stabilizing it for the future. And if you're above that weak layer, and you know, I mean, even if you're skiing it and you're doing like we saw of Alex's video where he's actually the skier was affecting the weak layer. I mean, stuff like that would help to stabilize that weak layer too. But if the slab is sufficient to keep you from doing that, then I think, you know, skier compaction's not doing much. It might give you more strength in that layer, which might help you to a certain extent. But it's all just a matter of load, and that's what I've seen. It seems like, you know, my years in Utah were very short, and they were a really long time ago. But I mean, the amount of loading you could get down there compared to the kind of loading that I've seen since I've come up here is just so different. And when you get that kind of loading, stuff that you never thought would come back to get you, comes back to get you really quick. You know, when stuff just comes kind of slow, it seems like people can just keep skiing and skiing and skiing. They're skiing on top of a weak layer, but you never get the big load that like knocks everything. And maybe part of the reason that they have some of the issues they do at Big Sky is that, you know, we might not get big snowstorms, but they get big windstorms up there, and so you guys do get the big load over short periods of time with the big hard slabs. Yeah.
But we've also crept up on deep slab instability slowly. You know, I'm not convinced, you know, obviously I get super nervous when we get a great big load quick. I mean, oh shit. But I also get nervous when we are getting long cumulative loading events and we have a known weak layer down there. And we saw that this year a little bit where we kind of crept up. And then we tipped the balance with a pretty good storm. But I don't know. We've crept up
Incremental
on
loading's
it.
not so good.
What's that?
Incremental loading's not so good.
Well,
yeah. I mean, it makes it, you know, it's a lot tougher to guess with
yeah,
incremental
it's harder
loading
to
than it is when
forecast
it gets
for.
big. Yeah.
But just because it comes in slow, if we have a persistent weak layer, it just seems like we get to a critical load and something will tip it over. And, you know, sometimes it's a big storm and sometimes it's not so big a storm.
Yeah. Anything else for you? Yeah.
What I kind of thought I heard Alex saying was that the skiers on the slab might be contributing to the hardness of the slab. Therefore, it would propagate more because it's become a stiffer slab, so to speak, because of all the skier compaction, not into the weak layer like your definition. Is that what I heard you saying? That maybe all that skier compaction is actually making the slab harder, therefore it might have the ability to propagate better.
Yeah, increasing.
It's kind of out there, but I think that's what I heard him saying.
Yeah, I mean, very theoretical.
I guess it's possible. You know, I mean, it depends on the kind of, you know, one of the things that I think helps to limit the size of your propagation is how variable things are. And so if you increase the amount of variability in that slab by the way that people ski it, that might, I don't know. Do you have any ideas on that, Alec? No, no good ideas. Lots of conjecture. Yeah.
I think there's probably some truth to that, as I'll show in a couple slides from Snowbird here in a little bit, but I think if you look at the post controls, like the one at Snowbird, I think was a naturally formed slab. I think it was formed prior to any skiers skiing on it. And then same with Jackson when they had their post controls. So I think, you know, a lot of the post controls are naturally formed events that are then triggered by
Yeah. Yeah, it seems like a lot of the post controls are sort of that first time opening type of thing. All right, so then that last step then would be overcoming friction, and Alec measured some of the crack face friction, and that really helps to explain this lower slope angle boundary for avalanche release. So we've gone through crack initiation, okay, then that crack growth up to a critical size, then propagation, and then overcoming friction. So those are our steps for an avalanche. And then let's talk a little bit about how those might relate back to post-control release. So for post-control release, just to remind you the definition that Scotty read out at first, avalanches that occur on a slope after mitigation measures have been applied and are not associated with significant loading. And so I just sort of went through these different steps and tried to figure out, well, what would be reasons for why we'd have post-control release. And so the first one is crack initiation. Perhaps that shot doesn't initiate a crack, or the crack size is subcritical. And that could either be a case of wrong charge, you know, perhaps the charge is too small for the depth of the weak layer and or the hardness of the slab. Another possibility is that it was the wrong place. You know, perhaps the explosive was placed in an area of stronger snow. Okay? And I think a lot with this post-control release, it's a lot of conjecture, right? And I'm just trying to think, okay, well, if we were unable to initiate the fracture, why would that be? Can anyone think of any other reasons why you might not be able to initiate the fracture? Why you didn't initiate the fracture?
I think you can also have changes potentially in the slab over time. So the situation that I've seen, I'm not sure it works as well in dry snow, is that sometimes a natural avalanche, I've witnessed natural avalanches occurring when they first go from the sun into the shade. And the slab sets, well, this is what I think is happening, and then we see release. So properties of the slab could also change.
Yeah. Yeah, and I have, you know, that's a really tough one because I've never seen it myself, and it's interesting because people will talk about it a lot, but then you talk to people that are up, at least in our snow climate, you know, like I've heard people say, oh, you know, stuff goes in the shade, maybe it'll avalanche, but then when you're with like the snow safety person and you say, oh, the sun's out on that slope, how are you gonna? And they're like, oh, I'm nervous about that slope right now. And then you say, well, how are you gonna feel when it goes in the shade? And they're like, I'll be psyched. When that thing goes in the shade, we're opening this thing up, you know. And so, you know, I've heard about those, but they seem to be fairly rare, at least around here. You know, but I don't know, they might be a totally different ballgame. But anything that changes the characteristics of that slab, and I think, you know, Scotty's got some discussion questions later about, you know, can just the sun change that slab, those slab characteristics? Yeah. Okay, wrong place, you know, was the charge placed in area of strength, and we just have another, you know, picture from Snowbird, and the shot was placed here, and later the avalanche was released here. I don't think this was post-control or anything, but let's see a couple pictures, or a couple videos from Lennon that Scotty gave me. We'll see the first shot go off. And this is a great one because this shot goes off, and then we're going to run another shot, a little bit downhill from the first one. So that first shot hole's up here. Takes out that first shot hole. So that's a nice one, huh? So this is the kind of avalanche that I've sort of called potential post-control release. Because it wasn't a post-control release, they hadn't finished their control work, but it was the kind of thing where it would have been pretty easy to say, well, we threw an explosive on that slope, and so we think it's good to go, but then someone hits a different spot. So that one seems to be, you know, either they didn't initiate the fracture with that first shot, or perhaps the first shot was placed in an area where it was less likely to propagate from. That's another possibility. Yeah.
It seems like that has some similar characteristics to well, what happened at Snowbird. You know, they shot the heck out of that place, and you know, an hour later, the 100th skier came by and triggered the thing. So maybe the explosives actually weakened or helped initiate some cracks under there that didn't grow to a critical size, but then
Yeah.
skiers pushed it just past
Pushed
the
it
point.
past that. Yeah, and see, that's one thing that we don't really know. It's like, when we place explosives on the slope, are we perhaps weakening the slope? You know, if we think that the critical size is only on the order of a meter or something, you know, and you're more than a meter away from that shot hole, you know, but we don't know. But that's actually, we could discuss that on and on, but I know Scotty's got that as one of the discussion questions for the panel later too, so we'll get to discussing. Yeah, Doug.
Well, the discussion panel, but that is a politically charged
Yeah.
issue, yeah.
It is, because you know, the lawyers want to know, hey, when you throw all these explosives on the slope, are you making it more dangerous for people? And ultimately, like, my response is, you're doing control work. You know, people are doing control work all the time. And if that control work was actually making the slopes more dangerous, we probably have a lot of post-control releases. You know, because, you know, there's a lot of cases where you throw 3 or 4 shots on the slope, and then you open it up and all these people are skiing it. And if you've actually made that slope more dangerous, it seems like we'd see more post-control releases. But that, again, is just, you know, conjecture. So another reason, possible reason for post-control releases is this idea of crack propagation. You know, the slab and weak layer conditions, are they conducive to fracture at that point that you do that? Now, remember, we need some kind of intact slab. You know, if we think of this in terms of the anti-crack model, we need some kind of intact slab to communicate that fracture. If there's a bunch of vertical cracks through the slab, that slab's going to have less capability of communicating that fracture outward, right? So, you can imagine a case where you put an explosive on top of the snow, and when that thing blows up, not only does it affect the weak layer, but it also puts a whole bunch of vertical cracks through the snow. If those vertical cracks are such that the fracture along the weak layer doesn't advance past this critical length, past some of those vertical cracks, we're not going to get that propagation to start moving outward. Does that make sense? And I think, you know, there's implications here for the air blast. I mean, a lot of the work Dan's doing is showing the effectiveness of air blasts in part because those explosives couple so much better with the air than they do with the snow. And he'll talk more about that in a minute. But with air blasts, I think also, you know, we're just kind of pushing down on the whole snow and maybe not breaking it up into as many pieces right away. And that might help us to get this, start winning this race. In other words, get that fracture along the weak layer moving out ahead of the uninterrupted slab so that the slab can do its work and help communicate that fracture. Again, this is just sort of, you know, possibilities. Any thoughts on that? Yeah, Mark?
I've just been thinking more about the snowmobile thing. You know, oh, big triggers like snowmobiles. It might be easier to trigger an avalanche. And just seeing the thing that Jameson started doing, I was thinking in terms of this, we oftentimes think, boy, when those guys are way up at the crest of their high mark, they are just cutting a trench into the snow. They've got to be affecting that weak layer. But at another level, they're slicing into the slab, and that track just chews through it. They're not. Maybe that's you know, who knows?
Yeah.
But it just may be one other thing that complicates how you trigger an avalanche with a snowmobile.
I think so. One of the things that I thought of is, okay, the snowmobile goes up. They create this slab fracture, right? When they go up and dig this giant trench, then they get stuck. Okay? Now their snowmobile is sitting down there below this thing, and they're standing on top of that slab. Now, it turns out that when you're on the edge of where you've cut that slab, your critical size crack that you need to get the propagation to occur is about half the distance as it is if you're just in the middle of an undisturbed slope. So now you're standing on the slab, and you're yanking this 500-pound machine out, right? While you sit basically on the edge of this diving board here, right there. You know, the thing looks like this. Your snowmobile's right here, you're standing right here, and you're yanking, pushing down on that weak layer, just daring it to move forward. And we see so many, you know, so many times where these people have snowmobiled up and down the slope, and then they trigger it while they're yanking their sled around. I don't know.
It
Just another thought that occurred to me.
Yeah, it fits nicely with why we're not seeing way more snowmobile triggered avalanches than skier triggered avalanches.
Yeah. Jay?
What I'm seeing a lot more of in Cook City now with machines on slopes is that they're not just high marking going up and turning around. They're doing these really long side hill traverses, a quarter mile, half mile through the Alpine. Like they're basically creating a crown as they're going and then turning downhill. So it's like a lot longer crack that they're initiating rather than just a point up and down. But you don't see these, they're not sliding.
Yeah.
It's kind of, but it's kind of like they're initiating it as soon as they make their turn, and then they side hill long distance and then turn out of it.
Which might make a case for, maybe the propagation conditions that just aren't quite there.
Right.
Or something like that. Yeah. I better keep moving because we need to move on to the other ones. But I just have one more thing that I want to talk about, and that is, one possible reason for the post-control releases in terms of crack propagation. Ron Simonhoys and I did some work at the 2008 ISSW looking at the changes in slab depth. And what Ron did, I thought, was really cool. He carved out these extended column tests and propagation saw tests so that we had thick ends and thin ends. And then he tried initiating the fractures at the thick end and then tried initiating the fractures at the thin ends. And what he found was, consistently, the fractures would propagate from thin to thick, but not always from thick to thin. And what that leads you to think of is, well, you got to be maybe pretty careful about putting explosives in areas that are too thick. So here's Ron. He's going to demonstrate this with a slab here, and he's got this slab that he's carved out like this. And start banging on this thing. And you can see it just left this chunk behind. But I think what happens is we're going from that thicker to thinner areas, that slab, it's easier for that slab to lose its ability to communicate that fracture. And, I think that's part of the reason why, often on these flanks of the avalanches, of course, they're often thinner. So here he's just got one that's going from thinner to thicker. And of course, the implication here is that we've always thought about thinner areas versus thicker areas, that we want to get our explosives in the thinner areas to initiate the fracture. But I think what this is at least suggesting is that there might be another thing going on. So it's not just that we're initiating the fractures more easily, but also that those fractures are more likely to propagate from those areas. And so this is an example from Copper Mountain Ski Area. They had 14 kilograms of ampho here, 8 kilograms of ampho here, nothing released. A person skied underneath this whole thing, and the entire thing was triggered. And including these, and if you start thinking, well, maybe we didn't affect the weak layer, or Ron went up here, and you can actually see the bomb crater right there, right? So the crater was affected. Now there could be a couple different possibilities. One is maybe the fracture didn't propagate as effectively from these thicker areas. Maybe those large explosives put too many vertical cracks through the snow. But in any case, this is an example of a post-control release where apparently, 24 kilograms of ampho wasn't enough to trigger an avalanche that a skier fairly easily triggered skiing across the thin spot at the bottom.
That crown was way thinner on.
Yeah, it thins out over here, huh? So they had, they were putting their ampho in the places that they thought were nice and thick, the meaty parts of the slab. Okay, so this is just repeating what I've already said. We know the thinner areas are places where it's easier to initiate the fractures, and it might be also easier to propagate the fractures. So the two things reinforce each other. And one other possible cause of post-control releases, I don't think this is a big one, but I don't think we can discount it, And this comes back to the comment, you know, could we possibly be weakening the slope by doing control work? Perhaps there's insufficient crack propagation. And this comes back to some work that I did a few years ago with Scotty and some other folks on looking at slopes that had already fractured but hadn't released. And so this is an example from Big Sky where in second dictator B they threw a shot right here and a big crack opened up across the top. And they skied down here and looked at it and they could see this really long crack. And so, if someone in the room was there, they could probably do a better job of explaining this. No? Okay. So there's this big crack through there. Well, you look at it and you think, okay, if we're talking about a critical crack size as a meter, and we've got a crack that's about 75 yards long or something, then we've clearly exceeded the critical crack size, right? And we haven't had an avalanche release. So is the slope more stable or less stable at that point? Any ideas? Hard to say, huh? Tough saying, not knowing. Well, they came down, I believe they came down then to here and threw another shot back in. Was that right, Scotty? Yeah. And then this one released the whole slab. Okay. So clearly, like, this was a case where we had crack initiation, we had crack growth, we had crack propagation, we had a steep enough slope to slide. But apparently the slab boundaries were still strong enough to maintain that cracked surface in place until that second explosive just happened to knock enough of the legs out from underneath it and trigger the slope. So there's a lot of complicated things going on here. It's a good thing we're running a seminar on this. So I threw this up for us to have more discussion on, but since I've gone over and we might need to just sort of move along, and I think we're going to have plenty of time for discussion today, and we also got quite a bit of discussion during the talk. So unless someone has one or two quick things before we move on to Dan.
Yeah, well, I got, 2 or 3 sessions ago with the National Avalanche School, partners kept emphasizing that there's a difference between